Hello all and welcome to Physics with Pranav. For those of you who are new here, I'm Pranav, a former CAIE Science and Maths student, an IGCSE and A-level physics tutor for students around the world, and an IGCSE world topper in science from back in 2013. This video is part of a series for the CAIE IGCSE curriculum, where for each chapter of the curriculum, I explore the key concepts tested, and this is backed by data from recent past papers. I dive deeper into these concepts so you have solid foundations in them. And then I show how these concepts are applied to past papers, which is what we'll be doing in this video. In particular, this video will look at questions from paper 4, which is a theory paper for chapter 3. That is a chapter on forces in motion from the CAIE curriculum. I do want to say that if you are an IGCSE student but are not studying the CAIE curriculum, don't worry, because a lot of the concepts that are tested in the CAIE curriculum read across to Edexcel and AQA and OCR. So by reviewing the concepts and by understanding how they can be applied to past paper questions, you're still going to be gaining a lot of value by looking at these videos. I do want to say that this video relating to chapter 3 is one of 3 videos I made for this chapter. If you want to check out the other 2 videos where I explore the key topics that I tested and the concepts around them, as well as how I apply these concepts to questions from the multiple choice paper or paper 2. Check out the links in my description so you can check these videos out as well. So with that established, let's now look at paper 4 questions for chapter 3. So we're starting off with the October-November 2023 paper. We're looking at the 42 variant, and we're going to look out for questions from the forces in motion topic. The first question is linked more towards measurements. So you've got your density and mass and things like that. Your second question is focusing on spring constants, which is a topic that we'll be covering. But part B of the question goes, Figure 2.2 shows a car traveling at constant speed around corner A on a road. So that's the car. This is corner A, that's corner B, and it's going around these bends. On figure 2.2, mark with an arrow the direction of the resultant force acting on the object as it travels around the corner. So essentially, we know that around the corners, the object is traveling on a circular path. And we know that there is going to be a force, a centripetal force, that ensures the car moves in the circular path. And that force is going to be acting towards the center of the curve. So if we assume that, I know obviously that the road becomes a bit straight here, and then you've got a tighter corner, a corner B. But if I was to look at the entirety of this, if I was to consider just that section, which includes corner A as a circular path, then you have to have an arrow that is pointing towards its center, and that's a centripetal force that allows the car to move around that bend. So that seems fine. Now they've said corner B has a smaller radius than corner A. The car travels at the same speed around corner B as it does around corner A. So state how the resultant force changes due to the car traveling around a corner of a smaller radius. So there's 2 ways to go about this, and I think the first easier method is to think about the formulae for the centripetal force. Now, this is not really introduced in your GCSE, so I wouldn't expect you to know this. But if you do happen to know this, then it is the product of mass multiplied by the square of the velocity divided by the radius, so it's proportional to that. And you'll find that the square of the velocity is directly proportional to the centripetal force needed to have an object moving in a circle. And the inverse of or rather you have an inverse proportion relationship with the radius of the curve, to the force needed to keep an object moving in that curve. So in this scenario, if we were to use the formula-based approach, we've been told that there is the same speed at both corner A and corner B. The only thing that changes between these 2 corners is the radius. Obviously, the mass, which is the other aspect of the centripetal force equation, remains the same between the 2 corners as well. So the only thing that really changes is the radius. And the fact that the radius gets smaller and it gets tighter means that you will need a greater force, a greater resultant force, to keep the object moving in the circular path. But of course, in your GCSE curriculum, this is not covered. So the way I would like for you to think about this is I would like for you to think about this in terms of an object that is moving around, say, the Earth, right? You can think of like a rocket to the International Space Station or any number of satellites that is moving around the Earth. You can even think about the moon, right? So the thing is, if you have an object that is moving faster, right? Eventually it will be able to escape the gravitational pull. And the gravitational pull in this case is equivalent to the centripetal force. So it'll be able to escape it, and we even have a term for it called the escape velocity. So if an object travels faster than the escape velocity, then it can escape the gravitational influence of a celestial body at a certain distance from it. So essentially, the fact that we're saying is the greater the velocity, the stronger the force of gravitational pull has to be to keep the object in circular motion. If the gravitational force cannot match the pull on the object, you're going to find that the object is going to drift into space, right? And we've said here that essentially here we don't really have a celestial object, and we're not dealing with gravitational force. We're rather dealing with a centripetal force that acts towards the middle of the track. But the analogy is that the faster an object is moving, for it to stay in the curve, you need a greater resultant force, a greater centripetal force acting towards the center. But in this case, the velocity is not what is changing. I think what is changing is the radius, right? So if the radius, again, is large, then if you think about it, then if the object is, say, further away from our planet, then in order to keep it within the gravitational influence of the planet, a greater gravitational force is needed. But if the gravitational force isn't strong enough and the radius keeps increasing, then the object is going to drift into space. And so I think the best example to think about that is you can think of a satellite of a certain mass traveling at a certain velocity. Now, it can travel, or it can be in orbit around the Earth, further from the Earth, than it can be around, say, the moon. Because the moon has a weaker gravitational force. So for an object with the same velocity and mass as that which is moving around the Earth, the further the object is away from the moon, the more likely that it won't be moving around the moon in a circular motion. Rather, it would probably just drift away from the moon because the moon's gravitational force isn't strong enough to keep the object moving, around it. Whereas if you have a scenario where you have the Earth, the object for the same mass and velocity can be further away from the Earth and can still be in a circular motion around the Earth because the force exerted by the Earth is strong enough to still act at that distance. So I know it's not quite a direct analogy, but I would like to think about, when I try to think about these situations, I usually try to think about analogies so that even if it's not very straightforward to you, by being able to think of an analogy, you can link it back to something that you are familiar with. So anyway, here with the tighter radius, the resultant force will be greater. So now move on to question 3. You've got in figure 3.1, you've got a boy who's throwing a ball at an object in a fairground. So that's the boy, that's the ball, that's the object. The ball has a mass of 190 grams and travels horizontally with a speed of 6.9 meters per second. So essentially going from left to right, that's 6.9 meters per second. So we've said that that is the positive direction of travel. So I want you to calculate the momentum of the ball. So this is straightforward. So if you want to calculate the momentum of the ball, you need to know the mass of the ball and the velocity with which the ball is traveling. So we happen to know both the mass and the velocity. The only thing that you need to do, obviously, is to convert the mass, which is in grams, to kilograms, because we want to work with SI units. The velocity is already in SI units, which is meters per second. So what I've done here is I've divided the mass by 1,000 because a kilogram has 1,000 grams. So if you've got 190 grams, then you're going to divide by 1,000 to be able to get the value in kilograms. And you multiply that by its speed of 6.9, and that gives you a momentum of 1.31 kilogram meters per second, or 1.31 Newton seconds. Again, the key is to always include the units, because even if you get the right value, which is 1.31, if you don't include the units, that's 1 mark off. So you're losing like 50% of the marks in this question for not including the units. So definitely they'll be looking at the formula for this conversion from grams to kilograms for this answer, and also the units. I think it's a bit brutal that they can cut an entire mark if you are not going to include the units, even if you've done all of the rest. So yeah, you don't want to lose marks for something as silly as that. So now they said after hitting the object, the ball bounces back along the same straight path with a speed of 1.5 meters per second. The object has a mass of 1.8 kilograms. Calculate the speed of the object after it is hit by the ball. So the way I'd like to think about these things is I always want to start with what is given to you and what you want to find. So in this scenario, you already know the mass of the ball and you know its initial speed. And now you know the final speed of the ball as well, and you know the mass of the object, and you know its initial velocity. So initially it's at rest, so it's not moving. So we have to, in these questions where there's always collisions involved, and you need to find the speed of an object or the direction in which it's moving after a collision. You always have to draw on the conservation of momentum, right? So if I'm looking at the conservation of momentum here, we have to say that the initial momentum of the system is equal to the final momentum of the system. And the initial momentum of the system is going to be the momentum of the ball plus the momentum of the object. And we know that because the object is stationary, there is no velocity there. It doesn't have a momentum initially, whereas the ball has a momentum. So we know that the total initial momentum of the system is equal to the total initial momentum of the ball. And we know what the initial momentum of the ball is, which is 1.31 kilogram meters per second or 1.31 Newton seconds. And that has to equal, by conservation of momentum, as we said, the initial momentum of the system has to be equal to the final momentum of the system. We know what the initial momentum of the system is 1.31 kilogram meters per second. The final momentum of the system is the sum of the final momentum of the ball and the final momentum of the object. Now we know we can calculate the final momentum of the ball because we have its mass and we have its velocity. That's what we've done here, 0.19 times minus 1.5. And the reason for doing that is because they've said the ball is traveling back in the opposite direction in the exact same straight line. And the fact that it has done that means it is essentially, we did mention at the start that the convention is, because they've said 6.8 meters per, or 6.9 meters per second here, for an object that's traveling from left to right, we have taken that the convention of a body going in this direction is essentially positive, whereas if it's going in the opposite direction, as it does after the collision, it's going to have a negative value. So the 1.5 meters per second would be negative, which we've got here. And then we know the mass of the object, we don't know its final velocity. So all we have to do is equate the initial momentum of the ball to the final momentum of the ball and the final momentum of the object. And if we rearrange the equation for the final velocity of the object, we get a value of 0.89 meters per second. Again, don't forget the units. I just want to draw your attention also to the fact that, between a 2-mark question and a 3-mark question, I think the only difference is in 2-mark question, it's usually just using a formula to be able to calculate the final value. You don't necessarily have to use a number of different formulae back to back. So it's not a layered question. It's rather a very straightforward question. You might have to rearrange. So for example, instead of saying calculate the momentum, they could have given you the momentum and given you the mass, and they might have asked you to calculate the velocity. So there might be a rearranging to have a subject of the formula. But for the most part, you will only be using one of the formulas for a 2-mark question, which involves a calculation. Whereas for a 3-mark question, you would be expected to use a number of different formulae, like, being able to not just calculate the momentum of each object, but also be able to say that the initial momentum of the system is equal to the final momentum of the system, and being able to correctly also point out that the initial momentum of the system is just equal to the initial momentum of the ball. And I think the third aspect here as well is the fact that you don't get caught out by the sign for this velocity because it's in the opposite direction. Now, if you do all of that, you should get your marks. And of course, don't forget your meters per second, because despite doing all of that, if you forget that, you are going to be losing a mark as a result, and you don't really want to do that. So I'm looking to see if there are any more questions on this topic. Nope, I don't think so. So if you move on to the next paper, which is October-November 2023, variant 4.2. So here we've got some nice kinematic questions. We got a question relating to work done, stopping distances. So we got a question around electricity, and they're talking about like convection and processes like that. So again, there's no questions around forces and stuff, and you got questions around like energy and eco-friendly ways of using energy and conservation of energy and things like that. So we go on to question 3, which is our question on forces in motion. A balloon of mass 15 grams is glued to a straw. Okay, so that's the straw, that's the balloon. The straw is threaded onto a horizontal string, so we've got that as well. The balloon is filled with air, and then the air is released, right? So the air is let go. Okay, as the air leaves the balloon experiences a force, which is fair enough. So this is Newton's third law, which says that every action has an equal and opposite reaction along the direction of the force. So if the air is going to come out in this direction, that is from right to left, we imagine that the balloon would experience an opposite force from left to right. Okay, so the balloon accelerates from rest until it reaches a constant speed. It then travels 0.67 meters in 0.81 seconds at this constant speed, right? Okay, so again here, we know the distance and the time that it takes, which means it's fairly straightforward to calculate the speed because speed is just distance divided by time, and we say the speed is constant, so that's straightforward. But let's see if you'd have to use that. That's the information we have at the moment. We've also got the mass of the balloon. So explain in words what is meant by the term impulse. So the impulse is the rate of change of momentum that a body experiences because a force acts on it over a period of time, right? So that's what the impulse is. The impulse is usually, as a formula, you can say that impulse is equal to the change of momentum, and impulse is also equal to essentially a force acting on an object over a period of time. I just want to correct here as well that the impulse is actually not the rate of change of momentum, it's just the change of momentum. Just noticed that, sorry. But it's true that it's a change of momentum when a force acts on an object for a period of time. Okay, so it's not the rate of change, but it is the change. So calculate the resultant impulse on the ball while it is accelerating. So we know that the impulse is the force multiplied by the time, or the final momentum minus initial momentum, as you will see in paper 2, for which again there's a link in the description. Many a time you need to choose which formula you're going to use for impulse, and again the formula that you use depends on the information provided in the question. So in the question, you know the mass of the balloon, okay? So that for me is leading towards using the change of momentum formula because you do use the mass there. And you do know that initially the balloon is at rest, although they haven't given that explicitly as a number. We know for a fact that the balloon is initially, motionless. So we know that. Now we know, as I pointed out here, we know that we can calculate the final speed that the balloon has because we know the distance and the time that the balloon travels and the speed, so we can calculate the speed rather easily. So the final velocity or the final speed is the final distance traveled by time taken to travel that distance, and that gives us a speed of 3.72 meters per second. And then we know that the change of momentum, if the mass doesn't change, which it doesn't in this case, to be fair, it's an interesting assumption to make in this particular scenario because we assume that we know that the balloon is losing air and we would expect that the mass of the balloon changes, but they haven't asked you to, they haven't given you a final mass, they haven't given you any statements saying that the mass is changing, so usually we can assume that the mass remains constant. So change of momentum is then going to be the final momentum minus the initial momentum, which is going to be the mass multiplied by the final velocity minus the initial velocity. We know the initial velocity is 0, so it's just going to be mass multiplied by the final velocity, which we've just calculated, and that gives us a value of 0.056 kilogram meters per second, or 0.056 Newton seconds. Again, always include the units. A key thing to keep in mind is that they have given you the mass to be 15 grams, so it's important that you convert it to kilograms so that you are working with SI units, which I've already done here. So I've got 0.015 kilograms, which is essentially 15 grams divided by 1,000. So just something to keep in mind so you don't get caught out. Again, the key things that they expect from this question is for you to be able to use, because it's a 3-mark question, you'll be using 2 different formulae. So the first formula you used is you've used the formula for speed or velocity, which is distance traveled by time taken to travel that distance. You've got that. And then you've got the equation for the change in momentum, again, where you plugged in the right values. One of the other things that they expect you to do is to ensure that you've done this conversion for mass so that you've got the mass in kilograms, and so that you're not getting caught out by using the wrong units. And then finally, of course, is using the units. You will lose a mark for that, irrespective of how much work you've done here. The third bit asks, explain how momentum is conserved as the balloon accelerates. So we know that initially the system is at rest, so total initial momentum is 0, which means we must expect the total final momentum to be 0. And we can expect this because you're thinking, right, okay, the balloon is moving, the air is moving, the air has a certain mass, the balloon has a certain mass. So clearly they will have a momentum of their own, right? So if they each have a momentum of their own, then the momentum of the air has to balance the momentum of the balloon because they would be acting in opposite directions. And that is essentially what we experience here. So when the balloon accelerates, the momentum of the balloon is equal and opposite to the momentum of the air released from it. So net momentum is 0, so momentum is conserved. So here we've got a nice question as well on essentially calculating the resultant force. So you want to be able to determine the magnitude and direction of the resultant force. So again, there are two approaches to this. If you are comfortable with the use of Pythagoras, if you're comfortable with basic trigonometry, essentially using SOHCAHTOA, then I would recommend that you just go ahead with the approach that I've taken here, where you create the vector triangle first. So to create a vector triangle, you have to have the two component vectors head to toe with each other. So in this case, they're not. So you've got the two toes sort of aligned there, but the heads are pointing in different directions. So here you have to either bring the horizontal vector down to the bottom here so that its tail is meeting the head of the vertical vector. Otherwise, the other option is to take the vertical vector here so that its tail is linked to the head of the horizontal vector. It doesn't matter which way you do it. I've done it using the first method I've described, where I've just sort of moved the horizontal vector down, and then the resultant will be going from the essentially the toe of the first component vector to the head of the second component vector. The other way I usually like to think about the resultant direction is through common sense. So you've got a force acting downwards and you've got a force acting to the right. So your resultant must be acting downwards and to the right, which is what our resultant is doing. So that's a quick common sense check to ensure that you've got your vector triangle correct. And once you've got this, if you're comfortable using Pythagoras and trigonometry, usually, well, not usually, the resultant is almost always the hypotenuse if you got a, if you got vectors at right angles to each other, component vectors at right angles to each other. So here you've got your resultant force, that is the hypotenuse. So the square of the resultant force is going to be equal to the sum of the square of the other two forces. So if you square that, and then you add that to the square of this, and then you square root the answer that you get, you will be able to get the resultant force through Pythagoras. So I've just said from Pythagoras, the resultant force is 0.84 newtons. Now, usually when they ask you to give the direction relative to the horizontal force, they expect you to provide an angle. So it's not just enough for you to say it's downwards and to the right. You've got to be able to give the angle. So I think the key thing is to always give the angle, but mention whether you're giving it relative to the vertical or the horizontal. So you could either give this angle here, or you could give this angle here. So I've decided to give this angle here as the angle to the horizontal for the resultant force. And the way I've done it is I've used trigonometry. So again, you've got all three sides, so you can literally use any of the ratios. But even without calculating, so say for some reason there's a typo in your calculator that you put in and you didn't realize, and your resultant forces value is say incorrect. I usually find it safer to use the values of these two forces because you know what their values are and you can be certain of it. And then by using the SOHCAHTOA, you got tangent, which says opposite and adjacent. So you got the opposite side and you've got the adjacent side. So you could just divide the opposite by the adjacent, do the tan inverse or arctan as some people refer to it, to be able to calculate the resultant angle, which I've got as 61.6 degrees. So it's 61.6 degrees relative to the horizontal. Okay, so in this particular case, they have asked you for the angle relative to the horizontal. Sometimes they can ask you for the angle relative to the vertical. So you just, again, you can use the tan ratio, but the opposite would now be the 0.4, and your adjacent would be the 0.74 Newton sides. So hopefully that makes sense. The rest of these questions are not related to forces and motion. Okay, so I'm gonna move on to the next paper. This is October number 2022, variant 4.3. got a question on kinematics or motion to start off with. Nice little question there. Ooh, you got a collision question. That's going to be your classic forces in motion question. So figure 2.1 shows a tennis ball approaching a tennis racket. The tennis ball hits the racket at a speed of 52 meters per second. So it's moving from the left to the right, and it's got a speed of 52 meters per second. The average force on the ball during the time that it is in contact with the racket is 350 newtons. Okay, so expect a question on impulse. The reason for that is you have been given a force during the time of contact, so that could be a question on impulse. The speed of the ball after it leaves the racket is 26 meters per second in the opposite direction to the initial speed of the ball, so that should tell you that that is going to be minus 26 meters per second because it's in the opposite direction to the initial 52 meters per second. And we've been given the mass of the ball, which is 58 grams. So again, we've been given a lot of information here. We know the mass, we know the initial and the final velocity of the ball, so we can calculate essentially the change in its momentum. We know that there is a force acting for a time period of 350 newtons. We don't know, we can't yet calculate just using impulse equals force into time what the impulse would be, but because the impulse could be is equal to the change in momentum, we can always calculate the time of contact if needed. But again, this is what I want you to start doing. I want you to start looking at the question, seeing the information that's given, and anticipating what kinds of questions you can expect. But I don't want you to obviously spend too long because you want to actually see what questions you get, right? So if I look at A, part 1, it says calculate the change in momentum of the ball while it is in contact with the racket. So this was a question we expected. We know the change in momentum is the final momentum minus the initial momentum. So the final momentum is going to be the final mass multiplied by the final speed. And you've got to subtract that from the initial momentum, which is going to be the initial mass multiplied by the initial speed. But we know that the mass of the object, in this case the ball, doesn't change. So you're just going to have mass multiplied by the final velocity minus the initial velocity. And you just have to be careful because the final velocity is going to be in the opposite direction to the initial velocity. So that's something to keep in mind. The other thing as well is to always convert to SI units. They typically catch you out by giving the mass in grams. So just make sure if it's in kilograms, you don't need to do anything. But if it's in grams, then you do need to convert it to kilograms, which is just dividing the value by 1,000. So I've calculated the initial momentum. I've calculated the final momentum, and I just need to now essentially subtract the two from each other. Now, the thing is, technically, I should have done the final momentum minus the initial momentum. But to calculate just the magnitude, you could do it this way because they are interested in the magnitude. So the key to keep in mind is that this isn't incorrect to calculate it this way. The reason I've done it is because it gives you a nice positive answer. Obviously, if you were to stick to the original formula I put in place, you'd have minus 1.508, and then you'd have that minus 3.016, and that's going to give you minus 4.524. And again, there's nothing wrong with that because your answer is still correct, your units are still correct, there's nothing wrong with that. But obviously, because they're interested only in the magnitude, I've just called it 4.52 kilogram meters per second because, again, the change is just the difference here. So nothing to worry about there. The next bit talks about state an equation which defines impulse in terms of force and time. So we know that impulse is equal to force in a time. So that's a classic 1-mark question. Usually it asks you to define some quantity. You could so sometimes they'd ask you to write the equation out straightforward. Sometimes they'd ask you to define it. And usually I've noticed in these definition-related questions as well. So if they ask you to define impulse, in these definition-related questions, you would still get a mark if you just wrote down the equation for it. So you haven't defined it in words, but you have defined it as an equation, and that is completely fine. If you want to be safe, you could do both. But obviously in this question, they are being very explicit, asking you to just state an equation. So the third bit is calculate the time that the racket is in contact with the ball. So we know that impulse is equal to force in a time. We also know that impulse is equal to change in momentum. So we know what the change in momentum value is, and then we know what the force is, which is given here to be 350 newtons. So all we have to do is equate this with this value and then make time the subject of the formula. Having done that, you get a contact time of 0.013 seconds, which is what I put down here. The last question, or rather question B, is asking you about the changes in kinetic energy. This is not a concept we've explored yet, but I will be making a video about this So we will be able to look at questions of this style there. So are there any other questions related to this topic? No, we look at things like temperature and specific heat capacities and energies and right, okay. So continuing on with May-June 2022, paper 4.3. This paper's got a very good question on resultant force, so we will be looking at that question. So there it is, 3A. Figure 3.1 shows a boat stored in a shed. The boat is suspended from the ceiling of the shed by 2 ropes. So you got 2 ropes, you got a boat. The ropes are forming an angle of 60 degrees with the ceiling, and they are essentially preventing the boat from falling. So they are countering the weight of the boat. The tension T in each of the ropes is 75 newtons. So that's 75 newtons. That's another 75 newtons. They want you to draw a vector diagram to determine the resultant of the forces exerted by the 2 ropes on the boat. State the scale you used. So here I have shown you how to use essentially both methods. I will say this, that I have not drawn this to scale, but I will talk you through the methodology that you would use to draw it to scale and to be able to calculate the values. Essentially, this is the method that they want. It's not very often in these questions they state the method to use. So in most questions, you would be able to use method 1 as well as method 2. So in this question, they explicitly ask you to use method 1. So we'll be looking at that. But I will also be showing you how you can use method 2 to be able to calculate the resultant force and its angle. So I think one of the advantages of using the scale method is the fact that you don't need to be well versed in trigonometry. And it's also the fact here that the resultant, when you draw the triangle out, is not a 90 degrees triangle. So if I was to explain the logic there, the first step always is to draw a triangle for the resultant force. So here you would have these 2 vectors head to toeing each other. So I've started off with the left rope, which has a tension of 75 newtons, and then I've linked it to the right rope, which also has a tension of 75 newtons. And then starting from the tail of the first vector, going all the way up to the head of the second vector, you've got the resultant, which is shown in blue. Now here, you don't have a 90-degree angle, and it can be explained quite easily. So we know that there is a 60-degree angle with the horizontal in the case of this 75 Newton vector. So if I drew a horizontal there, that's going to be around 60 degrees. And then we know that for this rope here on the right, which is another 75 Newton vector, again, you've got another 60 degrees with the horizontal. And then again, you've got essentially, by the basic rules of geometry, if you had a horizontal parallel line to that line there, then that angle formed with that horizontal line and this vector would be equal to the angle formed between this horizontal line and this vector. So essentially it's called the Z rule, or that's how I like to remember it. So that's going to be 60 degrees, and that would be 60 as well, giving a total sum of 60 plus 60 or 120 degrees. So that is clearly not, these 2 component forces are clearly not at right angles to each other, which is generally what we've seen, right? So in that instance, it is perhaps easiest to use the scale method. So how would you do the scale method? I think typically in the notes that I've been using, I've used a scale of 1 centimeter is 1 Newton or 1 meter per second. But obviously here you don't want to, you don't have space to draw a 75 centimeter line. So the better thing to do would be to state, say, 1 centimeter is equal to 10 newtons. So you could use the scale of 1 centimeter to 10 newtons, which means 75 newtons, you're going to have 2 7.5 centimeter arrows. So that's going to be 7.5 centimeters. That's going to be 7.5 centimeters. And then once you've drawn the vector triangle properly, you can measure the length of this blue arrow, and that would give you the value of the resultant. And they would also ask you for the angle. So typically you've got like a direction and a magnitude. So again, in this particular case, it's just vertically pointing straight. So you could always say that to define that clearly, you would say that would be at an angle of 90 degrees, or essentially perpendicular to the horizontal. So that is one way of defining it. But if you just wanted to be sure as well, if you placed your protractor's center there and measured this angle, which is the angle with the horizontal, you will find that it's 90 degrees. So it's quite easy to do using that method. So if you did draw it to scale, you will find that it will have a length of around 13 centimeters. Or rather, yeah, so it'd have a length of 13 centimeters. So that would be 130 newtons, because the scale is 1 centimeter is 10 newtons. And you can find that the direction of the resultant force is 90 degrees to the horizontal. But if I look at the other method that I've used, where I am going to use it using X and Y components. So what do I mean essentially, right? So if I drew out the vector triangle is going to be the same. It doesn't matter whether you use the scale method or you use the component method using Pythagoras and trigonometry, which is what I've shown here. So you would still have this triangle on the left to be your your vector triangle. Now again, because we've got a non-right angle triangle, one of the easier things I find to do is to actually split it into two right angle triangles. So I would have this right angle, I would have this arrow here, and then if I had another arrow that connects it there, then I would have two components, right? So for this particular 75 Newton force, I would have one vertical component and I would have a horizontal component. So that would be one of my right triangles, which is what I've got here at the top. So I've got the 75 degrees there, and then I've got its vertical component, I've got a horizontal component. And then you can do the same thing for the arrow on the top. So again, it's going to be pointing upwards like that. And that's going to have, again, a vertical component and a horizontal component, which I've drawn out as well. So you've got essentially two right triangles so that you can use your Pythagoras in a nice and neat way. And it also makes using your SOHCAHTOA a lot easier. And you can, so what you essentially do is you would add the vertical component of the first vector with the vertical component of the second vector, and you do the same for the horizontal components of the two vectors, and you'd be able to then find as essentially the resultant, right? So again, the resultant would then be the square of the sum of the vertical vectors plus the square of the sum of the horizontal vectors, and then if you square rooted the whole thing, you would essentially get the magnitude of the resultant. You will see in this scenario, you don't have to do such a thing because the horizontal components cancel out, which is consistent with what we would expect. But I will nevertheless take you through the logic. So I've called these vectors essentially, I've called this F1 and I've called that F2. And I've called the components F1x. So for F1, F1x is the horizontal component because x-axis is the horizontal axis, and F1y is the vertical component because that's the y-axis. And then I've done the same for F2, so I've got F2x and F2y. So the way to calculate F1x and F1y, because we need that to be able to then add together with F2x and F2y to be able to get the horizontal and vertical components of the resultant vector. So the way I would get that is I would use basic trigonometry now. It applies easily because you've got a right triangle. So if I wanted to get the vertical component, F1y, that is essentially linked by the sine ratio. So sine is sine of an angle. In this case, 60 degrees is going to be the ratio of the side that's opposite to that angle divided by the hypotenuse. So we know what the hypotenuse is. But we don't know what this side is. That's what we're trying to find. We do know that this angle is 60 degrees. So F1y is going to be equal to 75 multiplied by sine 60, because again, sine 60 is this side divided by that. So if I wanted to make this side the subject of the formula, I would just move the 75 and multiply it with the sine 60. So that gives me around 65 newtons. And F1x would essentially be using cos theta, because it's going to be cos 60 equals the adjacent divided by the hypotenuse, which means adjacent is going to be cos 60 multiplied by the hypotenuse, which is what I've done, and that gives me a value of 37.5 newtons. Again, sticking to convention, I've said that right to left is positive and left to right is positive and right to left is negative. Here we have the arrow going from right to left, so essentially that's given a negative value. And doing the same for F2, where again the opposite can be found using the sine ratio, and that gives you a value of 65 newtons. And the horizontal, essentially the opposite is being the vertical component, the adjacent being the horizontal component, can be found using the cosine ratio, and that's 37.5 newtons. But that's a positive value because it's acting from the left to the right. Now, if I wanted to find the total, the resultant force is horizontal component, I would just have to add the horizontal components of F1 x, essentially F1 and F2, or essentially I need to add F1x plus F2x. But these cancel each other out because they have the exact same magnitude but act in opposite directions, so there is no horizontal component. So the good thing is you don't really have to do any Pythagoras to determine the final resultant vector, because it would just be equal to the vertical component of F1 and F2. So the vertical component of F1 and F2 is basically F1y plus F2y, and they are the same magnitude, but they also act in the same direction. So essentially you double them, and that gives you a value of around 130 newtons. There's only a vertical component that exists, so you don't have to do Pythagoras to be able to, then you've got your vertical and your horizontal, and you don't have to calculate a resultant off the back of that, which makes it a little bit easier. But obviously, in this particular question, you would not use this method, because this method can only be used when there is, when it is specifically requested, or when no such thing like this is stated. And again, it probably is quicker and it probably is easier in this particular example, because you're using a non-right triangle, to just draw things to scale and use the scale like the one I suggested, for example, which is 1 centimeter is essentially 10 newtons. So hopefully that made sense, and we'll move on to the final paper, which is May, June 2022, paper 42. So if I go down, you go to question on energy and efficiency and power. So question 2, figure 2.1 shows a mass, an object of mass 2 kilograms on a bench. So that's this bit here. The object is connected by a rod passing over a pulley to an object of mass 3 kilograms. So this is essentially the system. The 2 kilogram object is released from rest and accelerates at 4 meters per second square. Okay. So what is the resultant force acting on the object? This is straightforward. Force is mass multiplied by acceleration. We know the mass is 2 kilograms. We know the acceleration is 4 meters per second squared. So if you multiply those together, you get a value of 8 newtons, that's quite straightforward. Part B asks, calculate the upward force F exerted by the cord on the 3 kilogram object. So again, this is quite straightforward, because if you think about it, in a connected system, the acceleration of the system has to be the same. So one way I'd like to think about it is, if a car is being towed by a truck, right? The acceleration of the truck will apply to the car as well, right? So this is very similar here. So the 3 kilogram object will then accelerate at 4 meters per second square as well, which means it'll have a resultant force on it, which is 12 newtons. Now, we don't know if that 12 newtons is acting upwards or downwards, so we're just saying resultant force would be essentially the balance, of the downward force and the upward force. So we don't know what the upward force is. We've called it F. We know the downward force is essentially the force of gravity acting on the mass of this object, which is the weight. And they've asked us to assume that G is 10. So usually, again, like I said, all papers before 2023, G is 10. I think since 2023, you have to work with 9.8. So then this object would have a weight of 3 into 10, which is 30 newtons. So that would be the downward force. We know that the downward force minus the upward force is essentially giving you a resultant force of 12 newtons, which means, if you rearrange these values, you'll find that the upward force has a value of 18 newtons. So that is the value of that force. So in part C, the objects have a constant acceleration. We can see there's a couple questions around the motion topic, which is chapter 2. Again, this is very common in paper 4s, where you will find that there are questions from a number of different topics that you need to apply together. And because we've done chapter 2, I thought I would just tackle these questions as well. So the first bit goes that C part 1, that is, shows the speed of the object 0.8 seconds after release is 3.2 meters per second, right? So this again is really straightforward, because they just want you to show that after 0.8 seconds the speed is 3.2 meters per second. And you've got a time, you've got a speed, and they've told you that the objects have a constant acceleration, and you calculated this acceleration to be, or rather it's given that the acceleration is 4 meters per second squared, right? So acceleration is the change in velocity divided by time. If you make the change in velocity the subject of the formula, then, acceleration times time gives you the change in velocity. The acceleration is 4, the time is 0.8, and the product of that is 3.2 meters per second, which is what we're after. The second part of question C states that a card of width 2 centimeters is fixed to the 2 kilogram object. As the 2 kilogram object moves to the left, the card passes through a beam of light that is perpendicular to the card. Okay, so it's a bit like a speed check, isn't it, or a speed gun? So using the speed given in C, part 1, which is 3.2 meters per second, calculate the time taken for the card to pass through the beam of light. Right, so you know the speed, it's 3.2 meters per second. Now here, the thing that you need to, the thing that you need to keep in mind is that if you want to calculate the speed of an object, using the method that's given here, where say you have a card or something attached to the object, the distance would be the width of the card, because you would have a certain amount of time over which, say, there is a laser, which measures the speed, and when the laser gets cut, say, by this card as the object passes, then it's going to measure the amount of time it takes, for this object to pass. And if you know then the length of the object, you will then be able to calculate the speed, because you know the time for which the laser was interrupted. In this case, a beam of light was interrupted, and you would know the distance that was traveled during that period of time, because you know the width of the card, which is essentially the distance. So here you've got an object that's moving at 3.2 meters per second. We already know that, so here we're trying to sort of reverse calculate what the time would be for the object to have passed or interrupted the beam of light. So the time would be the distance divided by the speed. So the distance is given in centimeters. That's not the SI unit, so always remember to work with SI units. So if it's 2 centimeters, if you want to convert it to meters, you have to divide 2 by 100, because there is 100 centimeters in every meter. So that is essentially a distance of 0.02 meters. And then, well, the speed is already in the SI unit, so 3.2 meters per second. So if we divide the distance by the speed, we get the time. So it takes around 0.0063 seconds, right? So very short amount of time, because it's not a card of a lot of width. So you can see that it doesn't really take that long for it to pass through at the speed that it goes, interrupting the beam of light. The rest of the stuff here is a scale diagram question, but it's relating to speed. But again, you would use the same concept, and I think here they're asking you to sort of stick to a scale drawing mechanism as well. This question around kinetic energy, which we'll be exploring. So I think, so we've covered the questions on forces in motion in this paper. And either ways, I hope you found this helpful. And if you did, please like this video and consider subscribing. I would also share this channel with others who you think will benefit from it. And thanks again for your time, and I'll join you in my next video.